Yep. Okay, and then come back to the microphone. Then you do the microphone so it's not on top of it. Sure. And then unmute the center one so I can talk about Harvard. So, all technology aside, I think we're actually ready. Everybody get enough pizza? It's too bad. All right, today we're going to listen to Armin talk about some concrete curling. It's been a major problem in pavements and industrial floor slabs ever since we've seen concrete used. So he's got some new ideas of how we can measure and combat that. Armin's been with us at the U of I for about half the time I've been here.
5 years.
So don't let it go to your head. Yeah. You haven't put in as much time as I have. He got his BS from Clemson on the other side of the continent.
Yeah.
Don't let that go to your head either. He's been studying with Professor Racer in the concrete materials. Plans on getting his PhD next summer. See what we can do to keep that from happening. So, I don't have much else to say. Let's welcome Armin.
Okay, so today we're going to talk about concrete, which is the more superior material. And I'm glad that all the people that do asphalt research are here so they can just experience the superiority of concrete pavements. So we're going to focus mainly on concrete curling, particularly in slabs, like industrial floor slabs or pavement slabs, and how fine, lightweight aggregates can actually reduce the curling that's experienced in the slab. We'll go over some of the literature, how we measured curling on a repeatable basis, and the results we got, and what we should do next. So since all of you deal with asphalt, you don't really have curling, so I'm going to explain it just very briefly. You can have curling due to temperature or moisture gradients. You see both in a field setting. So when you have a temperature gradient, if the temperature on top is a lot higher than the temperature on the bottom, it'll curl up. And with moisture, if you have a low RH on top and a high RH on bottom, it'll curl up like a U. And for this study, we were only interested in the moisture gradient. So everything that we tested was kept at the same temperature, and the beams we had were so small that no temperature gradient ever existed in them. So with curling in general, it is an actual problem in the field. These are field measurements taken on multiple slabs. The vertical lines indicate each slab boundary. And you can see this dominant U shape appearing in each slab as you take essentially dipstick measurements across the slab. And the deflection from the center of the slab to the edge of the slab in some cases goes up to 6 millimeters, which is huge because you only need about 2 millimeters of upward deflection to crack a slab under load. So 6 millimeters is not good. And this is just a jointed plain concrete pavement, so it does not have dowel bars. The dowel bars would definitely reduce this amount of curling, but curling has been seen even in doweled pavements because both slabs will actually bend up. So we thought we can utilize fine, lightweight aggregates to help address this. And these aggregates, especially the fine portion, generally pass a 3/8" sieve. They're very porous. They have an absorption of anywhere from 10 to 30%. And the stuff we used for this study was an expanded shale, which had an absorption of 14.6%. Normal aggregates only have about 1 to 2% absorption. So 14% absorption is very high. And we use this to sort of store water internally, which then gets later released as the concrete hydrates. And because the curling develops due to the moisture gradients, if we have this extra water in the concrete that's being released, we can hopefully reduce the gradient at early ages so it doesn't curl as much. However, let's say we had 2 companion sections sitting outside. Given a couple years, that gradient for a virgin section and a lightweight section would probably end up being the same. But it may not necessarily have the same curling value at the end. And we'll talk about that a little later. Yes?
Does it get
common practice to call the moisture curling warping?
Sort of. ACI has come up with some definitions, and they say moisture curling or temperature curling.
Okay.
Other people, yes, have used moisture warping.
Moisture curling is officially used these days?
Sort of. No one ever agrees on anything. So for the purposes of this study, curling only represents the moisture curling. No temperature, yeah. So the ultimate question is, can the lightweight aggregates affect this curling magnitude? No one's actually looked at this before. People have put these lightweight aggregates in concrete pavements. There's a large CRCP, a continuously reinforced section down in Texas, which had very good results because the internal curing through the lightweight aggregates actually caused the crack spacing to be longer and the crack widths to be very small compared to the virgin section. And specifically just looking at curling, Lay and Hansen have published several papers on how curing conditions can affect curling and how the moisture inside the slab or beam can affect the curling behavior. And Lay has published several papers showing that the curing duration has a significant role in the behavior of the curling in a beam. In fact, he found that the longer you wet cure a concrete beam, the more it'll curl once it's exposed to a drying environment. This is sort of counterintuitive where in concrete pavements you're told to cure it as long as possible to gain enough strength. Well, he showed and other people showed that curing it longer will get you better strength, but you may have a higher degree of curling. And we, as I'll show later, actually found similar results. And Hansen has showed that if you have a beam and you cast it, you place it in a drying environment and just let it dry from the top and don't supply any additional water, it starts to curl and then levels off. But if you continuously saturate the bottom of the beam so that there's always a source of water coming up through it, it actually continues to curl and curl because there's always water going in through it. So those two researchers and their papers led us to focus on certain things for our study. We realized that the curing duration was going to be a very important variable in this study and should actually be examined, and that providing too much water may actually hurt us because if we have a continuous source of water coming up through, it will just continue to curl and curl due to the pore stresses. So we can't just go ahead and add 100% lightweight and expect everything to be good. There needed to be some sort of balance for the lightweight that we add into the mix. So we developed a sort of factorial design. We looked at water cement ratios from 0.37 to 0.47. We added 18.6 to about 35% lightweight. That percentage is a volume percentage of the fine aggregate portion of the mix. And then we moist cured it from 0 to 6.5 days. All the specimens were covered for 24 hours before being exposed to any curing condition. So the one that had 0 days of moist curing was actually covered for 24 hours before being tested. You obviously can't test concrete just as you cast it. It needs to set. And so we chose a systematic circumscribed Box-Wilson design of experiments model to help us organize the three variables we were going to look at and to plan our different mix designs. So in the end, we had 15 different mix designs. We had 2 replicates for each mix design, and all the beams we cast and all the specimens we cast remained in the drying chamber for a minimum of 28 days. So this is a little diagram showing the Box-Wilson design. We have our 3 variables, the lightweight content, water cement ratio, and curing, and we have the 15 different points we're looking at. So this is just sort of a graphical representation. Not really important for you guys to focus on this too much, but just showing that we're testing sort of a cube or sphere volume of testing parameters. And now what are we actually measuring? We're going to measure the curling behavior of beams. We figured that a high aspect ratio beam would actually curl enough that we can measure the response accurately. We couldn't use a short beam because even though it'd curl, the magnitude of that curling would be so small it would be within the noise band of our LVDTs. So we used a high aspect ratio beam. They were placed sideways on a bed of marbles to act as a frictionless surface. This made creep and self-weight non-factors in our study. In a normal slab condition, you definitely do have creep and restraint, which add to the stress buildup in the slab. And we used 3 LVDTs so that we could get the deflection profile of the beam and compensate for any translation of the beam on this frictionless surface. So here's a picture of the inside the chamber. Here we have 12 beams running at once. We have the 3 LVDTs on each beam. They're sitting on a bed of marbles. They're sealed on 5 sides with aluminum foil to force a 1D drying gradient. We also cast some free drying shrinkage specimens, 3 for each mix. We cast using the geometry and tested using the method provided in the ASTM standard, but these were cured in the same manner as their companion beams. We didn't want to cure them according to ASTM because it requires a 28-day cure. We wanted to see how the drying behavior is changed along with the different lightweight contents and curing durations. And we also measured mass loss. Because these lightweight aggregates have a high volume mass ratio, we had to do the mix designs volumetrically to ensure that each of the 15 different mixes had the same exact paste content and aggregate content. We wanted to make sure we could actually compare all these mixes. So all these percentages are volume percentages within a concrete mix. And of the 21.8% volume of sand and lightweight, the numbers you'll see later on indicating, let's say, 18% lightweight, 30% lightweight, is 30% of the 21.8%. So just keep that in mind when these numbers are being tossed around. And just to get your head around the actual mix design, this is an example one. This is a mix at 0.42 wire cement ratio and 27% lightweight aggregate. And remember, the 27% is a volume percentage, and these are weights, so that's why it's not 27% right there. So once we had all these mixes and we could cast our beams and measure them with LVDTs, what do we actually get out of that? Well, we have 3 LVDTs, so we get 3 plots over time of what the beam is actually doing on that bed of marbles. And then using simple geometry, because we know exactly where each of these LVDTs is, exactly how long the beam is, we can convert that to a deflection. We plug the deflection into a simple mechanics equation, and we can calculate a strain. So we didn't have any strain gauges in any of these beams, but we can calculate the strain given the deflection of the beam. Now there's no real stress associated with the strain because there's no restraint, there's no self-weight, so it's just purely strain. So like previous mentioned, each mix had 2 replicates. So here's just 2 mixes we had. The little spikes you see in the data are actually pretty important. We'll get to that at the end. We were not expecting to see those, and it's very fascinating how they showed up. It's not a error in the LVDT. So we had 2 replicates. We would average the curve, and for any given mix, the average standard error was about 30 microstrain, which wasn't too bad considering each of these 15 different mixes had a different water cement ratio, lightweight content, curing duration. So that was nice to see. Once we had the average, we fit an hyperbolic curve to that average value. It fit very nicely, and there's a general form of the hyperbolic curve. There's no laser pointer. The top term, the strain ultimate is the ultimate strain that would be reached with that curve. The TH is the time to half of the ultimate strain. So those two factors, we get those two parameters out of each fit. T is just an arbitrary time within the drying duration. So we have a curve for each of the 15 mixes. So we're just going to plot a couple of the raw data curves. So here, the black curves have the same water cement ratio, same lightweight content, but different curing durations. In the red, same water cement ratio, lightweight, different curing duration. So if we compare these two, which have the only difference is the water cement ratio. So we have low and high. At a low water cement ratio, we get less ultimate curling than at a high water cement ratio. This curve continues on. I can't remember the exact value it ends at, but it's much higher than the low water cement ratio. But initially, the low water cement ratio has a high curling value. So already you can see it's a fairly complicated problem when you're trying to design a mix, because you have to think, do I want less early age curling, or do I want less long-term curling? And that would depend on the application. And when we decide the dashed lines are the longer curing duration, when we increase that curing duration, it shifts the curves up. So this matches well with what Tyler Lay saw when you cure a beam or a concrete mix longer and then expose it to a drying condition, you get more curling. And we saw that here. Another set of comparisons. All these have the same water cement ratio, all have the same light weight. The only difference is the curing duration. And as you see, the more you cure it, the more curling you get at longer ages. And here, we keep lightweight content the same, curing duration the same, but only change water cement ratio. So we see a trend as you increase the water cement ratio, you get more and more curling because you have more water that develops, or more water in the system. And the higher water cement ratios have a larger pore structure, which makes the evaporation or the diffusion of water much easier. So you have more water flow through the system as well. And finally, another comparison, changing just the lightweight content. And it's not exactly a nice linear trend. It seems that at low to moderate lightweight contents for this water cement ratio and curing duration, you get similar curling, but as you increase past some critical value, you get a significantly less amount of curling. So all this is very complicated because we have three changing variables. So how can we actually digest this information and come up with something useful out of it? Well, we can take each of those hyperbolic parameters that we found for each of the 15 different mixes and fit that to a model, and then we can predict curling behavior for any mix within these bounds here, because those are the bounds of the experimental design. If you go outside the bounds with the model that's generated, you get all sorts of weird behavior. So we used a generalized linear model using SAS to calculate all the parameters. And for the ultimate strain curling term, we have 5 parameters that are generated. Those are the coefficients. The significance of the model indicates how well it predicts the trends or the general behavior of the model. That is very good. The lower the number, the better. The adjusted R-squared value indicates how accurately it predicts the ultimate curling value. That's not as good. So we already saw from when we did this analysis that we wouldn't be able to actually predict accurate numbers, but we could predict accurate trends, which is really what we were after, because this is only one type of mix design using limestone aggregate. So obviously when you change aggregates, you're going to have slightly different behavior. So we didn't want to be able to predict sort of a design values. We want to predict design trends. And then we predict this term here, and these are 4 coefficients. Again, very good statistical behavior. And we come up with this. It's a hyperbolic form because you have a time times a unit and then a time plus a unit. And makes the curling strain at any time t a factor of water cement ratio, light weight, and curing duration. So this is very useful. Using this model, we can predict trends, any kind of trend we want to look at. Again, the magnitudes are not necessarily correct. So if the model predicts mix A has 150 microstrain and mix B has 300, that's not entirely accurate. But the fact that one is half the value of the other is accurate. So we can come up with cool plots like this. If we keep water cement ratio constant at 0.42, we can look at all possible curing durations and all possible light weight contents at 1 day of drying. And you can see the best performing mix is either low amount of light weight, high amount of light weight at a very low curing duration, which matches what we saw from the raw data. And then as we go to 14 days, that effect is sort of shifting. You can see that higher curing durations for any amount of light weight, you get more curling strain than you do at low curing durations. At 90 days, it starts sort of flattening out a little more. And at 365 days, you have a pretty steady state. Now, if we keep the light weight content constant and look at moist curing duration and the water cement ratio, we see at 365 days of drying, we get the best behavior at a low curing duration and a low water cement ratio. If we keep the curing duration constant, we see that at a high light weight content and low water cement ratio, we get the best behavior. So that's, and you could do this for any possible value in between those bounds that we set up at the beginning of the experiment. There's a gazillion different plots you can do. These are just several to show an example of what trends can be predicted depending on what you're looking at. So if your mix or if your project requires you to cure for 3 days, well, then you can look at what type of mix you should come up with to reduce curling. Again, this is only curling. It's not looking at strength. It's not looking at performance. It's just purely looking at curling. So the model is only applicable to mixes that have light weight in them. We can't extrapolate down to 0% light weight with this. So this model cannot be used to compare some mix to a virgin mix. And as we saw in general, the high initial moisture content leads to the highest curling magnitudes. So just some examples from this model. If you cure a beam for 0 to 1 day, it has about half the curling magnitude as the same beam cured for 6.5 days. And if you have a water cement ratio at 0.37, which is the lower end, it has about half the curling behavior as 0.47, which is at the high end, keeping the other two things constant. So this data only provides a partial picture of what's going on here. Again, these are not restrained. There's no stress being developed in these beams. There's no creep, which is an important factor in slabs because the self-weight from the slab causes creep, and restraint in the dowel bars or reinforcement that may be in there also causes a reduction sometimes or increase in stress depending on at what age you're looking at. So we also looked at the free drying shrinkage behavior to see if that matched up with what we saw with the curling, because there was no temperature gradient, so we knew any of the curling would be solely due to the moisture change. We did the same stuff for the free shrinkage. We fitted in the hyperbolic model, did the averaging, all that. Here are some of the coefficients we came up with. The model looks pretty good. Here's the time. Here's the TH coefficients. Again, the model looks good. And here's some of the raw data. So we have the free drying shrinkage strain. And as the curing duration increases, we see more free drying shrinkage strain. And here we have the lightweight content. I'm going to skip through that one because it's a whole lot easier to compare the curling strain to the free drying shrinkage strain. So the colors match up. As you can see here, at 6.5 days, we have the most curling and also the most free drying shrinkage. And the trend holds for the other two specimens. So the free drying shrinkage is also filling in part of this picture of if we have more water loss, we see more curling. All right. And same thing here. We have our 18%, 27% lightweight sitting around here. They're also grouped right there with a higher or a stronger free drying shrinkage strain, stronger curling. And the mix has 35% lightweight, has the least amount of curling and the least amount of free drying shrinkage. So the shrinkage model also helped us sort of conclude that the drying rate or the loss of water in the pores is very strongly tied to the curling that we see here. Now, as I said before, these models cannot predict to a virgin mix. They cannot be extrapolated down. So we cast some virgin mixes so that we could actually just directly compare to the results we had, because we wanted to see if this is actually better than adding no lightweight. So I need to ask you a question. Do you think adding lightweight helped the curling compared to virgin or hurt it? Anyone have a guess? So if I add 27% lightweight to my mix and I have another mix where I didn't add any, which one is going to curl more? Anyone have a guess? Lightweight. So he says lightweight's going to curl more. It depends on what age you look at. So the black lines are 0% and 27% with no moist curing. The virgin one shot up tremendously. It had the highest curling of any mix we tested, which makes sense. It wasn't cured at all with water. It has no internal water to help curing. So as that water leaves, the pore stress has become very high. And when we add 27% lightweight, we see a huge reduction in curling because we have an additional source of water, even though it wasn't cured, moist cured at all. But when we look at a 3-day cure, we get sort of a mixed trend here. It appears in the first 28 days, the mix with lightweight actually curled more than the virgin mix. However, it curled faster to a higher degree, but then leveled off. The virgin mix, which is the solid line, is going to continue increasing. As you see there, the ultimate curling strain it will reach at an infinite amount of time, usually about 90 days, is 282 microstrain compared to 188. That's a huge difference. However, at early ages, the lightweight is actually kind of hurting us a little bit. So, and these virgin mixes we only made two. We only made a 0-day cure and a 3-day cure virgin mix. But it seems to follow this inverse trend with respect to the curing duration. But more importantly, if we have a 0-day cure and we add 27% lightweight, and that's the only change, we halved the curling strain, the ultimate curling strain, that's a drastic change. The 3-day cure was not as drastic, and as you saw, initially the lightweight mix had more curling, but then it levels off, and the virgin mix continues to curl up to about 90 to 180 days. So, yeah, don't know why that one's in there. And the difference from virgin to lightweight, there's a lot of different changes. The modulus changes, which in a restrained setting affects the curling. But more importantly, in our setting, the increased hydration we get from providing additional water in the system causes the pores in the lightweight concrete mixes to be finer. The finer the pore you have, the more stress you get when it empties, but it's harder to empty the pore. So we have competing factors at play here. If you have a large pore, water can leave very readily, doesn't generate a lot of stress, but as the larger pores empty, it pulls water from the finer pores, and that pull is a lot easier to start than if you only have fine pores. It's a very complicated thing. People have spent their whole careers looking at the pore structure of concrete, and I'm just piggybacking on their research. So this is not really the focus, but that's a partial explanation as to why the virgin behaved the way it did compared to the lightweight. At the very near the beginning, when I showed the averages of the curves that we were taking and the little spikes in the data, well, those were unexpected. We were recording data, and we noticed that the chamber has its own defrost cycle. So every 6 hours, it kicks off the airflow to defrost the condenser coils. During this time, the humidity increases by about 10%. The temperature increases by about 1 degree. And it only lasts about 20 minutes before the system kicks on again. And just that slight change from the steady state system caused those spikes in the data. So the beam was responding to just that slight change in RH and temperature change. Temperature change we didn't think had a large effect because the beam is so small, there's really no gradient that would ever develop. But just that 10% humidity was, it was quite shocking that that had that much of an effect. So we decided to play around with that. So the black line is the curling strain of, in this case, a virgin beam. The red line indicates the humidity that the chamber is currently at. This says 0 days because this is when we started playing around with the humidity. But this beam had already been in the chamber at 50% humidity for 55 days. It had pretty much leveled out. It wasn't going to change anymore. So we first dropped the humidity to about 35%. There was some change. It's hard to see because of the scale. And then we increased it back to 50%. And we can see a very slight, again, it's hard to see because of the scale. We see a very slight reversal of the curling, which would be expected. The more water you add back into it, it should reverse the curling that happened. So we kept this at about 50 for about 7 days or so, just to get it to a steady state. And then we cranked it up very quickly to 80%. Cranking it up caused it to reverse the curling from about 190 microstrain down to 90 microstrain. So we reversed 100 microstrain of curling just by increasing the humidity for about 2 days to 80%. And then when we dropped the humidity to about 25% very quickly, it started to recover some of the strain it had, or the curling strain it had built up, but it then leveled off. Plenty of other research has shown that there is a lot of irreversible strain that can build up in concrete, and we're showing some irreversible curling strain that can build up in concrete. It was kind of cool because no one had ever really looked at irreversible curling strain. Most of the people were looking at temperature effects and how the temperature the concrete is placed at, it has sort of built-in curling. But here, we're just changing the humidity and we see this drastic change. This mix had no lightweight in it, had about 100 microstrain drop in strain when we up the humidity. We look at another mix. It's a different water cement ratio and different lightweight content, but it has lightweight in it. Now this scale has changed drastically. So it went from about 125 microstrain down to negative 150 microstrain. Huge drop, way more than the virgin mix. In fact, this went, it curls up as a U as we dry it. As you wet it, it curls back down flat. This actually went back the other way because we're now entered a negative curling strength. So it's actually going back the other way from 0. And 0 was just calculated from the start of the test. So that was quite fascinating to see as well. And this is, again, only a humidity change. We're going to look more into this. This is done like last week, so don't have much more of analysis. And these spikes right here are the defrost cycle as well. So it was interesting that we came up with this and saw this behavior. Okay, that's a lot of information. I tried feeding this all into Gavin with fiber optic cables into his head. He didn't really like it. Got a little upset. So I had to sit down and do this myself. How can we actually use this data that we presented? A lot of equations, lots of plots, lots of experimental runs. Well, we're just going to go through 2 examples, one with industrial floor slab and one with pavements, on how this model can provide guidance, but not necessarily the design criteria for a particular situation. Again, I want to stress, you can't use this to come up with, oh, I need 27.1% lightweight and a water cement ratio of this. This is just going to provide general trends and guidance for design. So in an industrial floor slab, we want to minimize curling because on floor slabs, they have steel wheel forklifts. If the slab curls up, the wheel hits the edge of the slab and spalls it and can even damage the steel wheel. And because this, let's say it's being constructed as the building is constructed, it really won't be heavily trafficked or loaded for about 28 days. So we need to minimize curling, which means we need a low water cement ratio. The high water cement ratios, as you saw from some of the graphs, resulted in higher curling values. We also know we need a high amount of lightweight to reduce that moisture gradient, and we need to cure it for a small amount of time as opposed to a long amount of time. Now, this will minimize curling, but especially this point number 3 here, if you don't cure it for a long time, it won't have a lot of strength compared to a longer curing duration. So you need to sort of take into account the fact that, yes, I want to minimize curling, but I still need strength for the surface because as those forklifts go over, I don't want my surface to deteriorate very quickly. There's no freeze thaw really, but those steel wheels can do lots of damage to concrete floors. At the same time we were measuring all these beams, we also did fracture testing on all the mixes at the same age and everything. And we found that even if you just moist cure it for 1 day, the fracture properties increase significantly compared to a no moist cure condition. So because of that, for industrial floor slab, the model would sort of predict or recommend that you cure it for about a day, use a low water cement ratio and a high lightweight content. Now, some of these floor slabs are sometimes covered with carpet. And if that's the case, the vapor transmission needs to be very low because if vapor gets underneath the carpet, it delaminates the adhesive and it starts falling apart. If that's the case, you'd have to look at the pore structure of the concrete and design it differently. Okay, so for pavement slab, minimizing curling is a good idea. It prevents some of the cracking that's seen with various loads when it's wet or dry. We'll just use the example. It needs to be a workable mix because we'll do, let's say, a white topping inlay on a horribly deteriorated asphalt pavement that should have been torn up decades ago, but someone wanted it there still. And we want to traffic it as soon as possible. So again, to minimize curling, we need a low water cement ratio. Not a problem with slip form paving. They use low water cement ratios. But if you're going to cast it in an inlay or use formwork, you need generally a higher water cement ratio to some degree. And if you look at the model, do all the runs, the higher water cement ratio is more sensitive to the lightweight content. So as opposed to recommending just one range of lightweight, you sort of get two ranges that would work, either a low amount of lightweight or a high amount of lightweight. We haven't fully looked at this particular situation. We're still working out the details on why a mid-range amount of lightweight would be a problem, but not a high or low. There's some critical, like, poor saturation level that's occurring at this point. And then the curing duration. This gets a little more tricky because industrial floor slab, we weren't really going to load it to like 28 days. So just naturally, even with no curing, the concrete would have a fair amount of strength just from 28 days of sitting there. But here, if we want to be able to open this pavement up rapidly, we'd want to cure it to some degree so it has enough strength. And based on the fracture testing we did at the same time, if we cure it for 3 days as opposed to no curing, we actually get about 20% more fracture resistance in the concrete material. So 3 days seems to be a nice value for this situation where you get enough minimization of the curling but enough strength. If you go past 3 days, like 4, 5, 6, then you get into, it rapidly increases the curling value. So in general, we would recommend, or the model would recommend these two sets depending on what situation you had. So slip form paver, low water cement ratio, high lightweight content, cure for no longer than a day, similar to the industrial floor slab. But if you're going to cast it and need that extra workability, you're going to have a higher water cement ratio, which changes the other two parameters. So those are just two examples of how this model can help guide the design of a pavement, but not necessarily provide exact values for mixture design. All these tests were done with a one-dimensional flow. So all these results are based on a 1D flow of moisture. Well, we wanted to make sure we actually had a 1D flow because, okay, we sealed it, but does it actually flow 1D? Does it somehow escape? So that picture doesn't show it well. So we cast some specimens with white cement and just the lightweight particles, and we introduced a UV dye into the mix so that we could trace where the water went over time. And these beams, or this beam right here, was exposed to the same drying environment as the curling beams. And it doesn't show up. So we cast this beam in 3 layers. This bottom layer, indicated by this line here, had no dye. It's just white cement. The middle had dye. The top had no dye. After 3 days, we get this. So we can see the bottom layer, there's some of the dye has creeped down, which would be expected because these were cast wet on wet. So there's already some bleed water that's moving before the concrete is set. But this down here is perfectly white. There's no dye, nothing. The top was the drying surface. At the top, this was originally all white, but all the water has gone up through and taken the UV dye with it and evaporated out. So this sort of confirmed, yes, we do have a 1D flow. We're not having water go in other directions. And so when we start modeling the moisture gradient, which I need to do for my thesis, haven't done it yet, we can very safely assume a 1D flow. We're not worried about water from here ending up all the way down here. And then when we apply UV light, we are confirming that the dye didn't go past about right here. It's hard to see with the projector. That's about it. Okay. Results, general trends, sort of beating a dead horse here. It does reduce the curling with respect to virgin, especially if you look at only longer curing durations. Longer drying duration. Curing duration is a very important factor. It affects the magnitude greatly. Similar things with the free drying shrinkage. So specifically looking at pavements, we've seen, or there's been research that used the lightweight in CRCP, had tighter crack formation, which is good. Can it reduce the joint opening and just the jointed plain concrete pavement? Who knows? Can you reduce the built-in curling that is used as MEPDG input? One study looked at what happens if you do reduce that, and you can decrease the thickness of your pavement by 1 inch just simply by adding this in. So that's a huge cost savings in materials. We had lower ultimate curling strain, and this would help us also in thin bonded overlays, because then the overlay wouldn't peel off of the horrible asphalt pavement underneath. It would just bond real well and protect anyone from driving over such an inferior material. And I ran through all that. This presentation was 107 slides, and we narrowed it down to like 70. So with that, any questions? Yeah, he toppled it on himself. Yes.
I got lost in one of your graphs.
Just one of them?
I think it's the very first one.
Oh, the very first. Okay, here, let's go.
It looks like your potato, yeah.
All right, let's
No,
go.
the
Oh, wait.
previous one. The very first one. Potatoes, bro.
This one?
Yeah.
Okay.
Yeah, on the left side. What's that?
Okay. Yeah, is the raw LVDT reading. So this is in millimeters. So for instance, the center LVDT is red. As we can see from the start of drying to about 25 days, it really doesn't go away from 0, which we would expect. Because if it's curling perfectly, the center should not really move. It should only curl outwards. Yeah. And then we have the left and right. But since it's not perfectly 0, it means the beam was moving slightly. But when we geometrically fit this data, we get the curvature.
I have a concern about one of the major assumptions in your study. I mean, you're doing it sidewise, right?
Yes.
For LVDTs.
Yeah.
I mean, and then you have to make the disclaimer all the time that we are not considering weight, we are not considering stresses and stuff like that.
Yeah.
Why not do it in the vertical direction?
Because that makes this calculation very, very, very difficult. Because you have liftoff.
That is true, but all the factors you calculate, they already incorporate the effect of weight there. Like all your equations, like C plus W, CW plus CW square, all of that.
Uh-huh.
I mean, I don't know anything about your research yet, so maybe you'll be able to convince me. But I have concerns about all those equations now, because the weight is not considered. And the behavior will not be like this. Like you saw negative curling.
Yeah, exactly.
Did we ever see it in the field before, right?
No. Well, if you have a very extreme, but yeah, you're right. What this does let you do is compare two mixes equally. So let's say mix A has half the curling strain according to this model as mix B. If we go take those two mixes, put them in identical situations in the field, let's say it's doweled, 10-inch slab, all that, we would expect to see similar results. Mix A would have less curling than mix B. It may not be half because, like you said, there's self-weight, there's all this, but it should most likely be less.
Yeah,
So
I have no questions about that. That is definitely true. But why didn't you just instrument in the vertical direction?
Purely because this equation becomes very difficult. Becomes very difficult to calculate the strain because you have liftoff from your subgrade. So let's say we place it on a perfectly flat steel beam, very rigid. It starts lifting off that beam. So the contact area is constantly decreasing.
Yeah.
But we don't know what it is.
But that's why you have marbles, right?
No.
There's no friction.
Yeah. But you're saying in the vertical direction.
Yes.
But in the vertical direction, yeah, it'd start leaving the marbles. Let's say you put them on marbles. If it's curling up, your subgrade response is constantly changing. How do we know what it's changing to?
We'll talk about
Yeah.
Yeah, but it would still ultimately be conservative then, wouldn't it? Because I had the same concern, especially based on this plot, because you said the beams were not fixed, right?
Mm-hmm.
So you see slight movement of the center LVDT showing that it wasn't fixed.
Yeah.
But then if you look at the one that's on the top of the plot, it's actually starting to revert back, which to me really just means pushing off of that LVDT and pivoting to favor the other.
Yes.
The other LVDT, because that's where you see that one continuing to accelerate.
Yeah.
So do you normalize one of the LVDTs to the other to determine that? Because if you were in the vertical direction, you wouldn't see it necessarily favoring that. Or if you assume a very rigid base course underneath it, then you would be able to see what happens when it does start to curl upward, creating that U, regardless of the actual contact area in the center of it. Likewise, when it reverts back and you would see the edge of the slabs pushing on it, it would tell you whether or not your slab is lifting off of your base material.
Yeah.
Because you see some of the negative numbers, but how do you know that would really happen? Again, it would be an assumption of an extremely rigid case, but more likely than not, your edge slabs, when it starts to revert back, the edge of the slabs would start to actually deform the base and not have as much lift in the center of it.
Oh yeah, like in a pavement setting, yeah,
Right.
obviously, yeah. So, but and going back to like the LVDTs moving like that, yeah, I put, let's see, I think it was like 15, these are spring-loaded LVDTs. So they do have some like minute amount of force on them. And the marble bed that these beams sit on, it's pretty frictionless. Like it takes barely any force to move the beam. So I put 15 of these spring-loaded LVDTs on one beam to see how much force, or how many LVDTs essentially was needed to actually like move the beam. It took about, I think, 9 LVDTs worth of, spring force to cause the beam to move. So
why didn't you just use unloaded no spring LVDT?
Because if the beam changed direction or it shifted,
Put it in another direction. Put one in here, one in here. So
But-
you measure this one over there, this one over there.
but if you have a free core LVDT and then the beam moves away from it,
Yeah, so that's why you have another set.
but then you
But now it's
stop,
two-dimensional.
yeah, you stop getting readings from this one. Yeah, the spring load lets us get readings regardless of where the beam moves. So there is some effect, but all these beams had the same effect because all the beams had the 3 LVDTs on there.
But does that exaggerate some of your
Oh.
strain readings and your deflection readings, especially if it starts to rotate, favoring the one on the bottom of this plot as opposed to the one on the top? So how do you correct for that? Do you normalize anything?
No, we don't. Oh, so you're saying like, oh, do we normalize, let's say, the center LVDT to make it?
If you look at the actual magnitude of the one, I assume these are the 2 extreme LVDTs, right? Or ultimately you ended up just having the 3 LVDTs, right? After your test of how many it took to move it.
Yeah,
You
we
just had the 3.
we had 3. Yeah.
So you've got the 2 on the outside. Are you really looking at, because you had some plots that ended up averaging them, is it fair to average the true magnitude of these when again the one is influencing the other?
I see what you're saying, but
And they're not perfectly pivoting above the center one.
exactly. Okay, I see what you're saying. Trying to think of a good way to answer this. When we take this raw data and get a deflection value, because That's all we need this for, is to get this term right here. We take the 3 points at a given point in time, plot it, and then fit a circle to that those 3 points. So that even if the beam has like translated or shifted, we are still fitting a circle to it, and the circle can like move to get the curvature of it. So in that way, then we calculate the chord and then the half chord or whatever it's called to get the deflection value. In that way, it's sort of normalizing this, but if the spring force was actually what was causing this to like move, then no, it wasn't accounting for the spring force of it. But it was accounting for any of the weird movement you would.
If you're looking at the radius of curvature and the
Yeah.
arc and everything, then that takes it into account.
Yeah.
How different would the conclusions be instead of beams? You would have done actual steps.
We would hope that the trends would be similar, and we're actually in the process of going to cast a couple slabs, because casting 15 slabs would be ridiculous. Yeah, we're going to cast real slabs, but we would hope that the trends would be similar. Obviously, the magnitudes would not be the same because these are unrestrained.
And how will you keep the slabs? What alignment will you do it?
What do you mean, what
Because
alignment?
the beam was done in this direction. Right?
Oh yeah. No. The slabs will have self weight and
Exactly.
yeah. So I mean the raw magnitudes, like if we calculate the curling strain of the slab, would definitely be different than any of these values. Yeah. But we would hope that the trend would be the same.
I don't know how the actual numbers would work out, but because you didn't have to worry about casting a slab and you're doing beams instead, would there be a significant advantage to casting quite a few more companion cylinders to add the factor of strength? Because if you go back to some of your colorful plots, which I thought is what confused Hassan initially, most of them have some symmetry to them.
Yes.
And so would the strength allow you to favor one side of that symmetry over the other and really maybe identify some sort of optimum?
Definitely. And we do have strength in the form of fracture properties like critical stress intensity factor, critical crack tip opening displacement, not like compressive strength or flexural strength. But these parameters are much better at describing the true behavior of the material rather than, oh, this flex beam broke at this amount. We do have all that for each of these mixes. And yeah, it's just not shown with this. But that could also help you, push you to like, well, here I can get low strain, I can use less lightweight, which is cheaper because it's another aggregate source. But if this strength is like half of this strength, well, okay, you know. So yes, that would help guide you again in another direction.
Last question. Does your father know about your elegant thoughts about asphalt pavements?
Oh yes, he does. Every time I talk to him on the phone, he asks me how do I still have a job because no one does concrete pavements. So I inform him that it's an art. It's a better material. It just takes a while for people to realize. So.
Wrap it up then. That's it. Thanks, Armin.
An hour exactly. At least an hour since I started the presentation.